Hi guys, today we're going to be doing a couple examples finding the domain of a function. We've got a couple of examples where the domain is not all real numbers. So these are the two major things you need to look for when you are finding the domain of a function, because these will result in numbers being thrown out of our domain because they do not result in an output that is a real number. So here's our first example. F of x equals the square root of 3x plus 2 minus 3. And we just have to remember what a domain is. It's all the set of numbers that we can plug in for x that would result in a real number. In the case of a square root, if we have a variable inside of the square root, we have to remember that this value, the entire value inside of the square root, has to be 0 or positive. It cannot be negative. If a number inside the square root results in a negative number, then our result would be an imaginary number, which is not real. So we have to make sure that the value inside of our square root is 0 or positive. So the way we do that is we just set an inequality, 3x plus 2, which is the value inside the square root, is greater than or equal to 0. And we solve that inequality, which is something we know how to do. We just subtract 2 from both sides and then divide both sides by 3, and we get x is greater than or equal to negative 2/3. So this just tells us that we can have any number that for x that is greater than or equal to negative 2/3 in order for our value inside of the square root to be 0 or positive. Anything less than negative 2/3 is going to give us a negative number inside our square root, and we want to throw all of those out of our domain. So you might be asked for set builder notation or interval notation. So here's both. Set builder notation just says the set of all x's such that x is greater than or equal to negative 2/3. Interval notation, our lowest endpoint of our interval is negative 2/3. Our highest endpoint is infinity. We use a bracket around the negative 2/3 because negative 2/3 itself is okay. That'll give us a 0 inside of the square root, which is okay. It will give us a real number output, and we put a parenthesis around the infinity because we always use parentheses there. Infinity is not a number, it's just an idea, so we can just think we are keep going and going and going and never reach infinity. So let's go ahead and graph this function and see if we can see on the graph an idea of our domain. Okay, so here's our graph. It looks like our function starts at this point, which looks like it's about negative 2/3. That seems like a reasonable answer, and it just goes up and to the right slightly. We can notice that there are no values of the graph that are to the left of negative 2/3, which would be less than negative 2/3. So having a domain of negative 2/3 to infinity is very reasonable for that problem. Let's look at another example. So here's my second example. It looks like f of x is equal to x squared plus 7x minus 8 over x squared plus 2x minus 15. So this is our other problem for our domain is if we have a function that contains a fraction, it's called a rational function, we cannot have a 0 in the denominator. Any fraction with a 0 denominator is considered undefined. We don't know what that is, so we basically need to find the values of x that will make this denominator 0. We don't care about the values of x that will make the numerator 0. That's okay. We can have 0 in the numerator of a fraction. 0 over anything is just 0, but any number over 0 is undefined. So finding the domain is basically boils down to setting the numerator equal to 0 and solving for x. And once we find those numbers that make the denominator 0, we're going to be throwing them out of the domain because they result in an output that is not a real number. So we're going to factor this. Oftentimes these problems are set up so that the denominator will factor. It's going to factor to x plus 5 times x minus 3 in this case. From this step we use the principle of zero products. That just tells us if something times something is equal to 0, then one of these two things must be 0 in order for that to occur. So we split it apart into two cases. Either x plus 5 is equal to 0 or x minus 3 is equal to 0, and then we easily solve those two to get our values of x equals -5 or x equals 3. So this is not the answer. These are just the values of x that will give us a zero denominator. So these are the values that we have to throw out of our domain in order to have a function. So here is our set builder and interval notation for our domain again. Our set builder is the set of all x's such that x is a real number and x is not equal to -5 and x is not equal to 3. In interval notation, we basically have to just go to those endpoints and use a bunch of parentheses to say that these endpoints are not in our set or our interval. So -∞ to -5 parentheses saying -5 is not in this interval. We're going to union that with -5 to 3, again parentheses saying that those numbers are not in our intervals. Union 3 to infinity with one more parenthesis saying 3 is not in our interval. So that is going to be our domain. We're going to look at our graph to see if we can figure out if -5 and 3 don't have an x value in our graph, which is what we're hoping for. So here's our graph. I'm going to go ahead and type it in, and we've got this curve, and we're hoping that -5 and 3 do not have a corresponding y value on the graph, and sure enough, it looks like at -5 the curve just bends steeply down, and it will just keep going and going down, never reaching -5, and this leg here is going to rise very quickly, approaching -5 from the left. It will never reach it. Same thing with 3. This leg will never reach 3 in the x direction. This one will never reach 3 in the x direction. So it looks like these two x values of -5 and 3 will never have a y value associated with them. So that's going to be our domain of our function. That's all for today.